Hello guys. Uh, First here I will introduce my name. My name is Infantri Siahaan from Mechanical Engineering of Udayana University. Today I will presenting about mechanical properties and strengthening mechanism. Let me see. And the friends, I take from this book, Metallurgy for the Non-Metallurgist, second edition, edited by Arthur C. Riordan. Okay, the main topic that we discuss in this section is mechanical properties and strengthening mechanism, such as solid solution strengthening, effect of grain size, cord working, Dr. Williams mystery, and other important strengthening mechanisms. The purpose of this chapter is to introduce the concept of mechanical properties and the various underlying metallurgical mechanisms that can be used to alter the strength of materials. Strengthening mechanisms are an important part of materials engineering, and metallic materials offer a wide range of options in terms of mechanical strength and ductility. Okay, the first, we can see mechanical properties here. When a force or a combination of force are applied to a material, the material responds by the forming or straining of in a complex manner. So we can see this equation is a stress equation from a material that correspond force. The concept of stress in its most general form is a force or load divided by the area over which it acts. For a force by F acting over an area A, and the stress is the alpha. The resulting strain depicted in the engineering stress-strain curve is the average or nominal linear strain, which is obtained by dividing the change in the gauge length, also called the elongation of the specimen, by its original length, LO. So here we can see the equation of strain, the difference of the final length divided by the original length, so we can get strength of a material. So we can see in the below the stress-strain curve. The intersection of the dashed line with the stress-strain curve determines the offset yield strength. So we can see the stress-strain curve in here. We can see offset yield strength. So here is the necking begins, and the final is fracture strength. Elasticity. In the elastic region of the engineering stress-strain curve, stress is linearly proportional to strain. This region is the straight line that can be seen on the left-hand side of stress-strain diagram. Plasticity. The point at which plastic deformation or yielding is observed to begin depends on the sensitivity of the strain measurement. In tests of materials under axial loading, three criteria for the initiation of yielding have been used: the elastic limit, the proportional limit, and the yield strength. So in this picture, A point is the elastic limit, and the A in here is the proportional limit, and the yield strength is the B point. Next, we can see here stress-strain curve of various alloys. You can see magnesium stress-strain curve, about bare aluminum alloy, stainless steel sheet, and nickel alloy steel. Next, here creep deformation. Creep deformation refers to time-dependent plastic deformation that occurs when a material is subject to constant nominal stress. The rate of creep deformation depends not only on the magnitude of the applied stress, but also on time and temperature. Continuing creep deformation over time ultimately leads to creep rupture, also known as stress rupture. The creep rate then reaches a steady state, which is called secondary creep. In third stage creep or tertiary creep, the creep rate begins to increase again and continues to increase until the specimen breaks. Okay, here we can see fatigue, tonus, and hardness. Fatigue. The tendency of a material to break under condition of applied cyclic stress is called fatigue. Tonus is the ability of a material to absorb an impact or shock load without fracturing. And the last is hardness, is the resistance of a material to plastic indentation. Okay, we can see the next topic is strength mechanism. The underlying structure of metals and alloys have an important bearing on their strength, ductility, and tonus. Strength of materials can be improved in various ways as described in the following section, such as solid solution strengthening, effect of grain size, and cold working. Solid solution strengthening is a mechanism that increases the strength of a metal through the careful addition of specific alloying elements, the insertion of substitutional and or interstitial alloying element produce a strength in the crystalline lattice of the host solvent structure because the solute atom typically have a different size than the host atom. You can see in this picture about small substitutional atom, interstitial atom, and large substitutional atom. So the result of this solid solution is distortion, or strain energy creates a barrier to dislocation motion. As a result, a moving dislocation is either attracted to or repelled by the solute. However, both situations result in a strength increase. Okay, next is effect of grain size. Grain boundaries are effective obstacles to slips because the slip of dislocation in the lattice of individual grains cannot easily cross the high energy barrier of grain boundaries. So, when we want make material strength, we can do from the grain size. Yeah, like that. And the next is cold working. Cold working greatly increases the number of dislocations during cold working. During cold rolling, the grains also become distorted. The grains and their slip planes try to align themselves with the direction of rolling as shown schematically in this picture. And you can see how a material be a strength material from cold working. Here is two underformed grains, and then the formed grains slip planes rotating, and the final is the formed grains broken slip planes aligning with rolling direction. Next is Dr. Williams' mystery. Dr. Williams' mystery cannot be solved for several years. The condition of precipitation hardening were not understood until 1919, when the theory and practice of precipitation hardening in alloys were published by America and his colleagues at the U.S. National Bureau of Standards. So this is the picture of precipitation hardening. We got zone 1, zone 2, and zone 3 here. In zone 1, submicroscopic precipitate particles are being formed as the alloy attempts to reach equilibrium. In zone 2, maximum hardness is reached. The solute atoms move about and form small particles attempting to form the precipitate. And the last is the zone 3. In zone 3, the precipitates grow in size with continued aging and tend to become non-coherent. Okay, that only I can presenting to all of you guys. Thank you so much for your attention, and